So you take a string, one end will be fixed on the wall and one end is held by your one hand. Now just pick the middle of the string and then leave it. Then what will happen? The string will start to propagate from the middle and it will vibrate in the form of a wave, and after a finite time, like after some time, it will come in the rest position again. So this is the very basic thing which we used to see when we were in, I think, 8th or 9th standard, like when we were kid. So in one dimensional, it is easy to analyzing this wave kind of phenomena. um, do you guys remember, like, just go on the bank of a river and take a stone and drop that stone in the middle of the, like, you just throw that stone in the middle of the river. So what happens? The water start to propagate, like it has some vibration, and that vibration is very uniform, isn't it? That vibration is very uniform, so that is also a wave kind of phenomena. In the same way, like if you take a color pollutant, that is a very famous example I used to give in all the classes. You take a color pollutant and you drop that color pollutant on the surface of a river, then that color pollutant start to propagate with the wave of the water. So that is also a wave kind of phenomena. And how it is formulated, then we are going to see the formulation of the wave. So in the vibrating string, the wave equation is simplified model for a vibrating string. Membrane. If you are going through these topics, so if you are curious to know about these kind of things, then you should just Google it. What is the membrane wave phenomena? What is the vibrating string phenomena or elastic solid? You should read it yourself. Are elastic solid in this physical interpretation, in this physical interpretation, UXT. What this unknown represents? This unknown basically represents the displacement of the wave. We already know that this unknown U represents the displacement of the wave. And if you drop the color pollutant on the surface of a river, then this U represents the density of the color pollutant. But since here we are just interested in the vibration of something, like the vibrating string or vibrating membranes or elastic solid, so U represents the displacement. And if you talk about even the density, so the density is displaced from one point to another point, isn't it? So we also call it a displacement. So in this physical interpretation, Ux comma T represents the displacement in some direction of the point x at time t greater than or equals to 0. Now, if we are talking about this wave kind of phenomena in a domain, so you can consider the domain. Since this kind of phenomena is in the universe, so we can't say that, oh, a domain is a finite domain or a fixed domain. We can't say that. It may have an infinite boundary. So what we, and it might be possible that in infinite domain the solution will break down. We don't know anything. So what we are assuming, that we take the subdomain of the domain and we assume that in this subdomain the solution is continuous, the solution is smooth. So let we represent any smooth subdomain region of U. So, although it is not possible to plot the whole U, suppose that this is something U and you choose a sub-region of this U, say V, and the U represents the displacement or U represents the quantity which is propagating, then what does it represent? It represents the quantity in this region, isn't it? If U represents if U represents the displacement or a quantity at any position x comma and time t, then the integration of U over this domain V over this smooth subregion V represents the total amount of quantity U in this subregion V. Now the acceleration within V is then given by, if integration of U represents this displacement over this region V, then what is the acceleration? If you know the displacement is this, then what will be the acceleration?
The second derivative.
Second derivative with respect to time. So the acceleration within V is then d2, and here you will get to know that why we are choosing a fixed subregion V, why we are choosing a bounded subregion V. We are going to see that integration V U dx. Now if you apply the fundamental theorem of calculus, then when first derivative will pass this integral, the integration of the upper and lower bound is going to be 0 in the case of fixed boundary. In the same way, if you will pass the second order derivative, again the integration of the upper and lower limit is going to be 0. So that's why we are choosing a fixed subregion, so that you can take, like suppose suppose you are in one dimension. You are in one dimension. So how you will represent? This will be x, isn't it? And this will be x1 and this will be x2. So this is going to be like this, isn't it? So this integration will be from x1 to x2 if this is your subregion. So and x1 x2 is a fixed number on the x-axis. So in that case, if you apply this, so this integration will go inside du over dt of dx, then plus the value of u at x equals to x2 and the derivative of the upper limit dx2 over dt, that is going to be 0 because x2 is a constant. So this technique has been used here. You already know that, but just to revise those things, I am explaining it again. So this will be integration of v u t t dx, and the next contact force is this capital F is force at any point x comma t. Suppose this capital F representing the force at any point x comma t or something like that. Then the net contact force will be the force which is varying around the boundary of V. Now the idea behind taking the negative sign is that we assume that the force is going outside of the boundary. Nothing is coming from the outside to, oh sorry, the force is coming from outside to inside, that like that is the outward unit normal is inward. Although we always say that in integration mu is a outward unit normal, but when we are saying that the force is coming inside, so it will replace with the minus sign, isn't it? So because of that minus sign is appearing, we are assuming that the force is coming like here, sorry, because this V is a smooth subregion, so force is coming from the out to in. Where capital F denotes the force acting on the subregion V through the boundary del of V, and the mass density is taken to be unity. Now Newton's law asserts that, see, the mass density is taken to be unity. So the Newton law asserts that the mass times the acceleration equals to net force. So mass time acceleration is equals to net force. Mass is unit, acceleration is integration over v u of t dx is equals to minus integration over del v f dot nu into ds. Now, if you will use the Gauss divergence theorem, the surface integral will reduce to the surface integral will reduce to the volume integral. So it can be written as integration of v u t dx is equals to minus integration of v divergence of v d of x. And this identity holds for any smooth or for any arbitrary. Say this is your equation. This charges equation star holds for any arbitrary smooth subregion V, and so you can remove this integration, sorry, utt is equals to minus of divergence of f. Now for elastic bodies, this force capital F is a function of the displacement gradient d of u, hence u t plus divergence of f is replaced with d of u equals to 0. Now for small du, the linearization f is a function of the displacement gradient. F is a function of the displacement gradient d of u, this force F. For a small du, the linearization F, that is function of du, can be written as, just we are taking the first term, is often appropriate, and so utt plus divergence of minus a du equals to 0. This a is a constant, so utt minus a divergence of d is nothing but Laplacian of u equals to 0. This is the wave equation for a equals to 1. Now just talk about if we talk about the elastic vibrating string, in that case the function f du will be nothing but it will exactly be equals to d of u in one dimension. So basically d of u over dx. So if you will be in one dimension, so this force f for elastic vibrating string will be exactly equals to du over dx. But since here we are talking the case in n dimensional, so that's why we have to use this linearization technique. So this is the wave equation for a equals to 1. Now this physical interpretation strongly suggests it will be mathematically appropriate to specify two initial conditions, because we have the second order derivative here on the displacement u and the velocity ut at t equals to 0 are required to specify the unique solution. Next we talk about the solution by spherical mean. For the wave equation, it is possible to directly solve the equation for n equals to 1, and for n equals to 2, we will use the method of spherical mean. However, for n equals to 1, we can directly solve it, and we are going to solve it for the case of n equals to 1, and that will give the derivation of the D'Alembert's formula. So basically, we are going to derive the D'Alembert formula today. Now, consider the initial value problem for the one dimensional wave equation in all R. And we have two initial conditions. As we can see that since the second order derivative of u is appearing, so we need two initial conditions to specify the form of the arbitrary constant. So here we have two initial conditions: u x comma 0 is equals to 0 and ut x comma 0 is equals to h. In this is defined in r cross 0 comma infinity, and this is defined on r cross t equals to 0. So say this is your equation number first. Where z and h are given. Now we desire to derive a formula for u in terms of Z and H. This is your equation number third. This is equation number first. This is equation number second. So we already know one solution. We can write it like del over del t plus del over del x del over del t minus del over del x operated on u. So if you remember in the previous classes we derived the solution of this form. This is a transport equation for A equals to 1. This was the transport equation for A equals to 1. We have derived the solution of this transport equation using the method of characteristic. Do you guys remember about that? So, say this is your equation number 4. Write V x t is equals to del over del t minus del over del x u of xt. So this is transport equation for A equals to 1. So if we know the solution u, we can write the solution of this equation number third. So from here we know that using the method of characteristic we can solve del v over del t plus del v over del x equals to 0. And what is the solution of this equation? So the solution is v of x comma t equals to a of x minus t for v x comma 0 is given as a of x. Is it clear how it is coming? Okay, if you have any doubt at this equation, then please do ask to me because this is a very basic and you need to know how we are writing the solution. So say this is your equation number 5, say this is your equation number 6. Now combining 5, 6 and 7, we obtain so this is Vxt equals to Ax minus t. So if you will use 4, this is 4, this is 5, this is unknown. If you will use 4, 5 and 6, then you can write del u over del t minus del u over del x is equals to v, and that is nothing but a of x minus t in r cross 0 comma infinity. Now you guys can see that this is again a transport equation. What is the difference between this transport equation and this transport equation?
The non-homogeneous term?
Exactly. So the non-homogeneous term, if you are going to use the method of characteristic, then it would be difficult to analyze this because we don't have the form of a of x minus t. If we had the form of ax minus t, then again we could use the method of characteristic. Since we don't have the form of ax minus t, then we are going to employ the another method to derive the solution via this method. So let's see what will be that method. This is a non homogeneous transport equation. Say this is your equation number 7. So here as a remark, or you can say that as a short note, I am going to give the form of a non-homogeneous transport equation. So consider the non-homogeneous problem ut plus b. B is a constant and this is divergence of u. This d is a way how LC wants to denote the divergence. Either you can write this or you can write this. Both are similar, so you don't need to confuse with this. Divergence of u is equals to f in Rn cross 0, infinity. Since this equation involves only for one derivative, so we need only one initial condition to single out the arbitrary constant in the solution of this equation. So we need the initial condition u x comma 0 equals to 0 on Rn cross t equals to 0. So fix x comma t belongs to Rn cross 0 comma infinity and set we are defining a function z of s is equals to u x plus sb comma t plus s for s belongs to r. Then z dot s. Now this is a test for all of you. If z of s is equals to this, then what will be j dot s? Basically d z over ds. Now if you will employ this d over ds on this, then we are going to use chain rules, and u is a function of two variables x plus sb comma t plus s. So the augmented variables are like x plus sb and t plus s. So how you will differentiate that thing? So just keep in your mind first del u over del x plus sb and then d of x plus sb over d of s, isn't it? Simply del. Then again del u over del t plus s del of t plus s is it clear? So del u over del x plus sb, this will be basically, since x is an spatial variable, x is a spatial variable, so this will represent divergence, isn't it, in your dimension? If x is belonging to Rn, then x plus sb will also belongs to Rn. So if x is a spatial variable in n dimension, so x plus sb will also be a spatial variable in n dimension for any constant s and b. So d of u is function of x plus sb. In your notes, I haven't elaborated these things. I have just copy pasted from the book so that I could explain in the class. And when you will differentiate it with respect to s, so it will be b plus u t into x plus sb comma t plus s, and the derivative with respect to s is 1. So you have, just focus on this equation star. You have u t x comma t plus b dot d u x comma t is equals to f x comma t, isn't it? Now what I will be doing, I will be performing just change the argument in the same fashion. Is it clear? You just change the x comma t argument to x plus sb comma t plus s in the whole equation. So if we use this one in this one, so this will be f x plus sb comma t plus s. It means z z dot s is nothing but f x plus sb comma t plus s, and as a result as a result if we are gonna integrate this function from minus t to 0, it means integrating this thing with respect to s, and this is minus t to 0 dz over d of s d of s. So this derivative will be cancelled out with this integration, and the upper limit will be 0 and the lower limit will be minus t. So z of s with minus t to 0 is equals to z of 0 minus z of minus t. Now just focus what is the value of z of 0 and what is the value of z of minus t. So as per this equation, the value of z of 0 will be u of x comma t, isn't it? U of x comma t. And what is the value of z of minus t? So if you will substitute z of minus t here, so it will be x minus tb comma t minus t is 0. So minus u x minus t into b comma 0, isn't it? Now this is u of x comma 0, and what is the value of u of x comma 0? It is z of x. So if we replace this argument with t minus b, so z will be function of t minus b, and we can pass this function to here. So this is u of x comma t minus z x minus tb. It means you have the form of the solution u x comma t is equals to z x minus tb plus integration minus t to 0 Isn't it? This is the solution of the given differential. Now, you know that the t is a time variable. It is varying from minus t to 0. So to get the relevant solution, we need to fix this. It was an approach to find out the solution. We can fix this. We will change minus t to t and order of the limit of integration, isn't it? So replace t plus s is equals to r. Replace t plus s equals to r. So when s will be minus t, r will be 0. And when s will be 0, r will be t. So and d of s will be d of r because t is a fixed. So u of x comma t is equals to z x minus tb plus integration from 0 to t f x plus, now s will be replaced with r minus t b comma t plus s is r dr. So the author was becoming more clever. He just said that, oh, he did not show up any kind of change of integration. He just replaced and put it as SS, and that is not going to make any. Even if you put now here as, it is not going to make any change, isn't it? So this is just a way. And so uxt is equals to divided by this solves the initial value problem star, isn't it? Now We are going to use this because this is the solution of a non-homogeneous transport equation, isn't it? Copy. I'm just gonna paste here and you will see how we can use it. So this is the solution, and what is the equation? Oops. So you can see that for this differential equation and under this initial condition, this is the solution of the non-homogeneous transport equation. Now, what is the value of B in this non-homogeneous equation?
-1.
B equals to -1. F equals to f of x comma t equals to a of x minus t. Let's just put the condition. So u x comma t will be z, and we have given the initial condition. Yeah. Am I making any mistake? 0 equals to 0. Yeah, I forgot to write G in your notes, and I am searching where is Z. So just make your correction in the notes. I was preparing the notes in the night, and sometimes I do the typos by hand. So I forgot to write, sorry. X minus t into -1 plus integration from 0 to tf, that is a, x plus r minus tb, x plus r minus t, and the value of b is -1, and t is replaced, comma r is replaced with minus t, so minus r, d of r. So z x plus t. Oh, I have written, but I have written it b, not z. I have written it b, not z, and there is a reason, because we are saying that for this first order equation u of x comma 0 equals to b of x. So I'm writing it b. I have written, yeah, I was in my mind. Plus 0 to t a x minus r plus t minus r d of r. So b x comma t plus integration 0 to t. We will use the initial condition which was given initially to calculate the form of a and b. To calculate the form of a and b. X plus t minus 2r dr. Can I erase this? So this is your solution. Now to express it as a single function of y, what we are taking, y equals to x plus t minus 2r, then the lower limit will be giving, like when r equals to 0, y will be x plus t, and when r will be t, y will be x plus t minus 2t, that is x minus t, and d of y will be minus 2 of dr. So dr is minus 1 over 2 dy, isn't it? So it will be b oops x comma t plus minus dr is 1 over 2. I am taking a g. For 0 it is x plus t, and for t it is x minus t, a of y dy. Just change the order of integration to x minus t to x plus t. So this will be b of x comma t, and when you will change the order of integration, minus will change to plus 1 over t x minus t to x plus t a of y dy. This is u of x comma t. Let's substitute the initial condition given to find out the value of a and b. So is it clear till this step? Where we have b of x equals to u of x comma 0. Now the first initial condition in equation third gives. So what was the first initial condition? Let's copy this initial condition. This is the initial condition. This first condition will give us u of x comma 0 is equals to b of x equals to z of x, isn't it? And let's copy this solution as well. And it came like b of x plus t, so don't put comma, just put x plus t. B of x plus t plus 1 over t x minus t to x plus t a of y. So this will be z of x plus t plus 1 over 2 x minus t to x plus t a y dy. Now still we are left to derive the form of a of y. I am explaining this phenomena in very detail because I have uploaded one assignment today and you have to use this to derive the form of the D'Alembert formula for that assignment question. So each detail is very necessary. Now the second initial condition, that is ut x comma 0 equals to h, and equation number 5. So what was equation number 5? This is the equation number 5. And equation 5 implies a of this equation number 6, not 5, sorry. A of x is equals to v of x comma 0 is equals to ut of x comma 0 minus ux x comma 0. So ut of x comma 0 is given h of x and ux x comma 0 will be g dash of x. X belongs to R. So say this is your equation number 8. Now substituting it in equation 8 gives u of x comma t is equals to z of x plus t plus half integration from x minus t to x plus t h of y minus z dash of y d of y. So this is the derivative with respect to its argument. So its derivative will cancel out with the integration. So it will be z of x plus t plus 1 over 2 integration from x minus t to x plus t h of y dy, and this derivative will cancel out with the integration, so it will be minus 1 over 2 z of y from x minus t to x plus t. So it will be z of x plus t minus 1 over 2 z of x plus t, and when this minus will pass, so it will be plus 1 over 2 z of x minus t plus 1 over 2 integration from x minus t to x plus t h of y dy. So this is the D'Alembert's principle now, and if you have any doubt, then please ask. Now I am coming to the rare fraction time. Is it clear? Okay. So this is the conservation form. This is the conservation form of this given first order partial differential equation, where A is the derivative of the flux function, where A is the derivative of the flux function. So for the time being, we assume that the flux function is a convex flux function. So the second order derivative of the flux function will be greater than 0. So for convex flux function, the second order derivative is greater than 0. It means A dash of u is greater than 0. It means A is monotonically increasing function, monotonically increasing function. Now when we derive the solution of this first order Cauchy linear partial differential equation, then we came across the point that the solution is given by u is equals to u naught x minus t a of u, isn't it? Yeah, and since this is a solution of the given Cauchy linear first order partial differential equation, so its derivative, its partial derivative with respect to t and its partial derivative with respect to f should be a continuous function. It means it should not have a discontinuity. So when we derived ut, we came across the point that this function is and the same ux is u naught dash over 1 plus t a dash of u naught dash. Now we can see that as soon as this denominator becomes 0, the solution will break down in a time t. And we came across the point that for a convex flux function, this a dash is greater than 0. So in that case, to become this 0, we have to have that u naught dash is less than 0. U naught dash is less than or equals to less than 0, strictly less than 0. So it had to be monotonically decreasing. So if for a convex flux function u naught is monotonically decreasing, so if for a convex flux function your initial data is monotonically increasing, the solution will break down after a finite length of time. The solution will break down after a finite length of time, and that critical time is represented by t of c equals to minus 1 over a dash u naught dash, that is known as critical time. Next, we are going to talk about the two kind of problem. One, conservation law with monotonically decreasing initial data, and one conservation law, scalar conservation law with monotonically increasing initial data. And we are going to study the Burger equation. So what is the Burger equation? The Burger equation is basically if you take a heat flow in the pipe, so if you take the heat flow in a pipe, then the temperature of the fluid, if suppose you take a pipe and you just put some fluid at one end and it start to flow in the pipe, so the temperature of that fluid will start to decrease with the displacement, like the rate of change of the temperature of that fluid will be negatively proportional to del T over del S, how it is spreading in the fluid. And if the pipe is not isolated, if the pipe is not isolated, then the fluid will also, the temperature will also change from its end. That is basically the temperature will also change from its end, or you can say that the temperature will also change with the viscous of the pipe. So del T over del S is also proportional to the second order derivative of T with respect to S. I am not getting where I have written the Burger equation derivation. I think I wrote the derivation, isn't it? Yeah. So it means del T over del T is proportional to minus T of del T over del S plus del 2T over del S square, and we remove this proportionality constant with 1. This is viscous term. So del T over del T plus T del T over del S equals to. Now if you assume that there is no change in T because of the diffusion or because of the viscous term, so this term will be 0. In that case, it will reduce to the first order Cauchy linear partial differential equation, and that first order Cauchy linear partial differential equation is known as Invisib-Burger equation. Is it clear? Now we are going to talk about the solution of this Invisib-Burger equation with different kind of initial data. So we have two kind of initial data. Either initial data is sufficiently smooth in all the domain, or the initial data has one point of discontinuity. So if t x comma 0 is equals to t naught of x, smooth initial data, then if a conservation law, in the conservation form, how we can write it? Equal to 0. If a conservation law t square over 2, I think, yeah, conservation law is defined with a smooth initial data, then we call it a Cauchy problem. And on the other hand, if the initial data has one point of discontinuity, it has one point of discontinuity at x equals to 0. If the initial data has one point of discontinuity, then it is known as Riemann problem. So we are going to discuss this Burger equation with the Riemann initial data in the case when it is decreasing, in the case when it is increasing. So do you guys have any doubt till this point? Is it clear? No. So what is the flux function here? Is it convex or concave?
Convex.
Convex. So in what condition we will get a smooth solution and in what condition we will get a non-smooth solution?
If the initial data is increasing, the solution is smooth, but is monotonically decreasing is continuous
So
solution.
this initial data is monotonically increasing or not? You can simply check that at x 0 and then it is increasing to 1. So it is monotonically increasing, isn't it? It means the solution is going to be a smooth solution, isn't it? It means we will be getting a rare fraction solution. So firstly, let's plot the initial data. Say this is x, this is your u naught. Because t is fixed, t is taken to be 0. T is a fixed number here. So at x less than or equal, so this is 0 comma 0. When x is less than or equals to 0, the initial data is 0. When x is, suppose this is alpha comma 0. So when x is varying from 0 to alpha, this is a straight line. So it is u naught equals to 0. This is u naught equals to x over alpha. And as soon as it becomes greater than alpha, it becomes 1. Is it clear? Now just solve this given differential equation. So how we will solve this? We have to discuss only this case, because in this case it is going to be constant 0, in this case it is going to be constant 1. So when you will write the solution, we are becoming very clever that u of x comma t is equals to 0 when x is less than or equals to 0 is equals to 1. This needs to be defined, what will be when x is greater, because this will be identified with the solution of the differential equation, what will be x greater than or not. So first solve this. For the interval, Ivan, are you in the class?
Yeah, of course.
Because this thing I am explaining just because of you.
Yeah. Thank you so much.
So for the interval x when varying from 0 to alpha, dx over dt equals to u naught of xi, where u of x comma 0 equals to u naught of x. So this is defined as x over alpha. So this will be your xi over alpha, but that is another case when we will discuss. So when you will solve this, it will be x equals to u naught of xi t plus the constant xi, that is xi equals to x minus t u naught of xi. And what is the value of u naught xi? If you will focus, u naught x is x over alpha, so u naught xi is xi over alpha. So this will be x equals to xi plus u naught xi is xi over alpha into t. X equals to alpha xi plus xi t over alpha. Just take xi outside. So alpha plus t over alpha. So xi will be alpha x over alpha plus t. Now, if you combine this with u naught xi equals to xi, so this will be gives u equals to u naught xi, that is xi over alpha. And what is the form of xi? So just let me give the numbering. This is equation number first. This is your equation number second. This is your equation number third. And u of x comma t. Along these characteristics, u of x comma t is u naught of xi. That is your solution. Say this is your equation number 4. This is your equation number 5. So in view of equation number 4 and 5, 4 gives u x comma t is equals to u naught xi, because the solution is going to determine with the help of the initial condition. So initial condition is u naught of xi. Xi is a function of x comma t. And what is the form of u naught? The form of u naught is xi over alpha. Now just substitute xi here. So alpha x over alpha plus t over alpha. So x over alpha plus t. In the region are such that x is varying from x to alpha and t is greater than 0. Now the most important part of this solution is coming, how we will be defining the domain, because I haven't given the domain. So that is the most important part. What you said? You said that the solution is going to be smooth, isn't it? You said that the solution is going to be smooth. So this is x over alpha plus t. What will be the lower limit? The lower limit is 0, because as soon as x will be approaching from left and x will be approaching from right, it should be 0. So x over alpha plus t. But how you will be defining the upper limit? So when you will be approaching from left and when you will be approaching from right, you should get 1, because the right limit is fixed. this when you will be approaching from the left of this, suppose this is some beta, when you will be approaching to beta from the left, and this will be x is greater than beta, when you will be approaching to beta from the left, and when we will be approaching to this function from the right of beta, so this should be equals to 1, but this is a fix, isn't it? This is a fix, so right limit when x equals to beta is 1. When in what condition, at what value of x you will be getting the left limit as 1, when this beta will be alpha plus t, when this beta will be alpha plus t, in that case x will be approaching to alpha plus t and the left limit will be approaching to 1, isn't it? So this is alpha plus t, and as soon as it is bounded by 0 to alpha plus t, this x will be greater than or equals to alpha plus t. Is it clear? Again I am asking. So totally clear, or still you have doubt? If you have doubt, then please to ask. So this is your solution. If you are not asking, then I am assuming that it is clear to you. And if you have doubt, then please to ask, because this domain is very important. So when you will be approaching from left of this domain, it should be equals to the value of 1, and when it will be giving 1 when x is becoming equals to alpha plus t. So the upper limit of this, the upper boundary of this x should be alpha plus t. In that case, you will be getting the left limit equals to alpha plus t. So because of that, we are getting the boundary alpha plus t, and as soon as it becomes alpha plus t, x will be greater than alpha plus, put equal sign here. Now, this is the solution of the Riemann problem when you have this initial data. If you take alpha equals to 0, in the case alpha equals to 0, the solution will be 0, x over t, 1, x is less than or equals to 0. Let's draw this solution. The drawing was also a very important point which you guys were missing, isn't it? So, along the characteristic dx over dt is equals to u naught of xi, that is equals to 0 when x is less than or equals to 0, and dx over dt, that was equals to u, that is equals to 1 when x is greater than alpha plus t. In between, it is u naught xi, so it is going to be x over alpha plus t between. Now the point is that how you will plot this, how you will plot this. So we are going to plot this solution in xt plane. So this is the solution. Now if we want to plot this solution in xt plane, oops. This is your x-axis, this is your t-axis. So what will be the gradient, what will be the slope of the line? dt over dx, isn't it? If dx over dt is 0, then what will be dt over dx? That will be infinity. And what at what theta tan gives infinity? 90 degree. Tan pi by 2 is infinity. So when theta angle is 90 degree, You are getting this, like when x is less than or equals to 0, your characteristic has slope 90 degree, isn't it? So these are the characteristics line across which u equals to 0. These are the characteristics line across which u equals to 0, and alpha is suppose some positive quantity here. Now when x is greater than or equals to alpha plus t, so this is the line x equals to alpha plus t. When x is greater than or equals to alpha plus t, in that case u equals to 1 and dt over dx equals to 1. At what angle you get 1? 45 degree. So tan 45 degree you may mention here. So these are the characteristics that is making 45 degree to give you u equals to 1. The rest of the solution is going to lie in between these things, and the solution is going to be u equals to x over alpha plus t, and the characteristics will start to emanate from here. It will not intersect basically, and gradually it will converge, and it when 45 degree will be coming, it will be fixed. Is it clear? Yvonne?
Yeah.
Is it clear now?
Yeah.
Okay, so this was the case.
Thank you so much.
Oh, yeah, I think you are in. I think that you are not in the class.
Yeah, I'm in the class actually. Yeah.
Okay, so this is the way how we are plotting the solution. If still you have doubt, then please work out on this, and then we have one case of shock wave. So in the next class, when I will be finishing the next part of wave equation, we can cover the shock wave. Okay. As soon as this alpha will approach to 0, in that case you will see that this plotting will be like this. Alpha is 0, so it will be a centered rarefaction wave, isn't it? A centered rarefaction wave, and then it will start like this. So there will be a centered rarefaction wave. So this is the plotting, how we are plotting. Please go through these things, and yeah, in the next class we can discuss these things. Okay. Yeah, so I'm assuming that you guys know everything. Okay, bye. See you in the
Thank you so much.
Bye.
Bye.
Bye.